Hey all, successive substitution is a useful math technique that you're going to want on your project, so let's take a look at how you can use it, because I did a brief informal survey and I don't think that you've been taught this method yet, but it's really useful. So suppose you would like to solve the equation natural log of x is equal to the base 10 log of 3 times x. That's implicit in x, so there's no way that you're going to be able to rearrange that and isolate it so that x just equals a bunch of numbers. So if we wanted to solve this by successive substitution, the first thing that we would do is rewrite this equation. And the rewriting that we would do would be to isolate one of the x's. One x on one side of the equation. It doesn't matter which x, whichever x you think is more convenient. So it could be the one in the natural log or the one in the base 10 log. So for example, one way that we could do this would be that x would be now the exponential of log base 10 of 3x. So I haven't tried to isolate the x on the right-hand side, but I've just isolated the one on the left as just a value of x. The next step that we're going to do is we're going to call this one a special kind of x to distinguish it from the other x. We're going to call this x xcalc. Right? So xcalc will be the one that we just isolated over here. We're going to call the other one xguess. This one. The one that's inside of here. There can be more than one xguess, right? If it was a bigger function, you can have xguesses all the way out through here. It wouldn't matter how many different xguesses showed up on the right-hand side. We could have as many as we wanted. The method of successive substitution, let me put my window back there. I just bumped it over a little bit. The method of successive substitution, as the name would imply, is we're going to guess a value, we're going to substitute it, and then we're going to successively do that until we have our answer. So our next step is to do exactly that, right? Pick a value for xguess. Once we have our value for xguess, we're then going to, as the name would imply, calculate our value for xcalc. So for example, let's assume that our first value of xguess that we're going to guess is 0.05. Let's just do 0.5. That'll be easier. So 0.5. I'm then going to calculate xcalc as being equal to the exponential of log base 10 of 3 times the guessed value, right? 3 times xguess. That will be my calculated value. So we'll come up with a little set there. If I were to throw that into a calculator, right, it doesn't really matter what calculator I'm using. Almost any calculator could calculate that. I will end up with a value of 1.1925. The fourth part of the successive substitution method is the part that decides whether or not you need to keep going, right? The successive part of that. So if you find that your xguess is about the same as the value that you just calculated, great, you're done. How do you decide if it's close or not? It kind of depends on the problem that you're solving, right? Just go until you think that you've got the precision that you need for the problem that you're interested in. Otherwise, the successive part of successive substitution means take the value of xcalc that you just made, turn that into a new value of xguess, and repeat. So the otherwise portion here is that you will now update xguess to be equal to the value of xcalc that you just made, and then we're going to repeat it. Repeat this process over and over and over again. So let's assume that we continue this table right here. The next value of xguess will be our previous value of xcalc, so 1.1925. So if we're building up this table, this value just came over onto the left-hand side. We can now use that value in our expression for xcalc, so we plug in 1.1925 right back into the same expression, and we'll end up with a new value for xcalc, which is 1.7395. Right, so this was our update step. And now we calculated a new value of xcalc to be 1.7395. 1.7395 is not particularly close to 1.1925, so we would do it again, except now our new xcalc will become, our new xguess will become our old value of xcalc. So I'll just copy that number here, 1.7395. So again, I'm going to update my value of xcalc, my value of xguess with a old value of xcalc, and now I'm going to repeat that calculation, and I end up with let me make sure my colors are accurate here, 2.0494. So that's my new value of xcalc. I'm getting closer, right? The size of the difference between the guessed value and the calc value is now a little bit less than it used to be, but it's not terribly close, so I would probably keep going. I can go as many times as I want, all the way down through here. Let's say that I go all the way down until eventually I find that I have 2.3223, and then I would calculate a new value of xcalc and get 2.3234. Right, so in between there were a bunch of successive substitutions, right? I kept getting a new value of xcalc and plugging it into xguess, et cetera, et cetera. I'm going to say that that's close enough, right? I don't have a strict definition of what's close enough for this problem. You can define it as you need it for most of your problems. So what we have just done is an example of successive substitution. What we've got over here in the far left column that I haven't written is a number that we call an iteration. An iteration is which step of the successive substitution method you happen to be on. So the very first iteration that we did was this one here, right? We iterated from our initial guess over to our calculated value. That was one iteration of this method. We then went on to do a few more iterations. This was our second iteration here. We went on to a third iteration here, and then I skipped a few steps here, but you can get the idea, right? This is all the way down then to our 10th iteration. So after about 10 times of the successive substitution method, we have now come up with a set of value, or a single value of x that seems to be pretty consistent. There's no reason we have to stop there though, right? We could keep going if we wanted to, but we chose to stop. These values over here, if you take this value, and these values, assuming there were a bunch of other ones inside of there, these form a vector. And this vector indicates our convergence. Convergence means how close have you gotten to the point where things have stopped changing, right? They have converged on a stable value. And so you can create a plot that is very useful to decide if you are close enough by plotting your xcalc on one side and your iterations on the x-axis. If you do something like that, for this particular example, as we'll see in a moment, there was sort of a ... through here, and then if we had continued out through here, we would see that it flattened off. And it had actually flattened off here at about 2.3234, which is the same value, if you rewind a little bit ago, that we would have gotten if we had used something like fsolve, right, or a calculator or something like that. This plot is called our convergence plot. All it is a plot of xcalc as the iterations proceed inside of this method. And so the nice idea of this, excuse me just a second. Sorry about that. The nice idea of this particular method is it's not complicated to code. So let's take a look at what this would be like inside of MATLAB if we wanted to code this particular approach. I've got the general setup here. So there's a couple of elements that I've already provided. One of which is the visualization part here, right? The plot of our convergence profile has already been handled for us. I've given us the answer up here, which is x, and I've defined the problem up above here. The part that might be a little bit new to you, and the part that I've already completed here, is a for loop, right? The idea of taking one value and replacing it over here, and then calculating, and then replacing, and calculating, and replacing, and calculating, that lends itself very nicely to a for loop. So let's see how we could set something like this up in order to do that successive substitution procedure for the aforementioned problem. The first thing we want to do is set up what kind of successive substitution are we going to do? How many iterations are we going to do? So the number of iterations that we're going to do, we're just going to pick a number, right? It could be 10, it could be 100, it could be 1,000. I think 10 will probably be enough for our particular example. The other thing we're going to do is a step that's called pre-allocation. So we want to have an idea of how many answers we're going to have before we actually start our procedure. So I have a feeling that we're going to expect a vector of a bunch of numbers that have a number of entries equal to the number of iterations, right? If you look back at the vector that we just generated a moment ago, it would be 10 by 1. And so similarly, this vector is going to be 10 by 1. Then we're going to start our calculation procedure, right? And the loop over which we're going to perform this calculation is from 1 up to the number of iterations, right? We're going to take a for loop and apply a number of steps, eventually equal to the number of iterations that we want, so 10 steps. We're going to calculate a new value of x based on our old value of x, the guessed value. So in order to do that, we have to make a guess. We're going to take our first guess outside of our for loop, and our previous guess that we had said in our sort of hand solution that we did a minute ago was 0.5. So we're going to get started there. Once we're inside the for loop, we're going to calculate a value based on that x value, or sorry, that x guess value, which is the exponential of log base 10 of 3 times x guess. Right? This is what we did on our hand calculation, and we would like to assign the result of this to be xcalc. That's exactly what we did in our hand calculation. The one caveat is we want to store these values, right? We want them to build up over time. And so we're going to assign that to be the ith value of xcalc. And that way, as I goes up, we keep adding numbers to the bottom of our vector and filling them out. The successive part of successive substitution is the for loop. The substitution part is once you've calculated a value, now make that your x guess. So this is a little sort of a strange statement if you've never made one before. We're going to assign to x guess our previous value of xcalc, which is xcalc of I. Right? So each time this line 14, comes up, we're going to take the value of xcalc that we just made, and we're going to assign it to xguess. The loop will then come back around to the top, and it will use that xguess to produce a new value of xcalc, and then it will plot it. So let's go ahead and save this and run it and see what our plot looks like. So there we have it. Let's get rid of our title there. Our title looks a little bit, oh, we forgot to specify which calc we need. So let me update our title there. There we go. So you can see from our convergence plot that we started off down here. After the first step, we made a big improvement, right? We got closer to the result that we were after. And each successive step that we take gets closer and closer and closer until you're out here around the 9th and 10th iteration, where it really hasn't changed very much. If we wanted to up the number of iterations, we can do so just by changing the number of iterations here. If we rerun this code, you'll see that really after about 15 steps or so, there's no appreciable change anymore. And so this is an example of successive substitution for solving a single problem. The real utility of this comes when you have a recycle loop inside of your system. So as an example of this, let's look at a previous homework problem. Let's scroll this down a little bit, give ourselves a new page. Problem 2.3 from a previous homework had a system that looked something like a CSTR in the middle. It had a separator over here. We would feed some material into our reactor. It would go to our separator. We would get a little bit of product out. And then we would also take some material from our separator and run it back around like this. The labeling that we had, the stream here was 1. Excuse me, that one was 0. Into the reactor was 2. Out of the reactor was 3. The product was 4, and our recycle was 1. And as you'll recall from setting this one up, it was a little bit tricky because you had to do a material balance around each step and then put all of those together, and you'd sort of get this big old equation that you would then have to solve for one unknown. This can be very easily done with successive substitution without having to do all of that algebra. The way that you do this for successive substitution is to break, and I put that in quotes because you're not really breaking it. You're only doing that as an approximation here. Break the recycle. So by break the recycle, what I mean is don't ignore it, just don't have the recycle come all the way back around like this. Instead, erase the recycle here and break it so that recycle comes out over here. And now we change these to be very similar to what they were before. This value over here on the left, let me write it here, would become our moles of A in stream 1 that we're going to guess. Right? This is still our stream 1, but this would be referred to as our guess of stream 1. This stream is now our 1 calculated. Right? And so if we had to calculate a moles of A in this particular stream, we would refer to this as moles of A in 1, but this is the calculated value. So successive substitution says whenever we will have a guessed value of Na1 that's very close to our guessed value of Na1 calc, we have solved this problem. And so the advantage of this is that the solution procedure follows from left to right. We guess a value of Na1, which would be here. We combine it with whatever we know about stream 0, and then we calculate stream 2. There's no iterations involved in there. We solve our reactor problem. For this one, it was a CSTR. Using just the available information from 2, we don't have to do too much for there. Once we have 2, we can use the reactor information to get 3, and then once we have 3, we can use our process specs to now get this new value of N calc, right? This is our Na1 calc, and then we repeat, right? We go back to where we used to be, update our guess with our calculated value, and proceed in such a way. If we wanted to look at a couple of these iterations, the way that we had in our previous set, if we wanted to look at sort of an iteration table here, let's make this our table, and we can count up our iterations over here. The first thing that we're going to do is we're going to guess a value of Na1. Once we have Na1, we can calculate everything from stream 2 as Na2 is equal to Na1 plus, Na0, which is our feed, plus Na1 guess. And I'm just going to move these a little bit closer over to my previous value just so that we have some more room to work with here. We can then get Na3 as a function of Na2. That's our reactor problem. And so this would require a material balance on the reactor, which we have the solution for that. It's in the homework solutions. We're not going to detail it here. And then we found out in this problem that Na1 calc will be equal to 0.6 Na3. And so that will be the last step that we've got. And then we'll compare our Na calc over to our Na guess. So our first iteration, if we don't know how much Na happens to be in 1 to guess, probably guess with a 0, right? Maybe there's nothing in the recycle. If we were to add these two together for that problem, this would have been 19.455. And then we could apply our knowledge of the material balance on the reactor to calculate Na3. This would have been 2.683. And then we take 60% of that to determine what our Na1 calc is, and we find that it's 1.6101. Successive substitution says, okay, take that value, turn that into your next value of N guess for your next iteration. So we bring that value down and say 1.6101. Right, so this, I'm not sure I can draw a straight line that far. Here was our update. Right, so the substitution part of successive substitution, take your old value, make it your new value. We could calculate a few new values here, so this would be 21.0651. This one ends up being 2.949. And finally, we end up with a new value of Na calc as 1.7699. That's not bad, right? The first step we changed by almost 1.5 moles, a little bit more than that. Our second iteration was quite a bit better. If we go on to one more iteration that we do sort of quote unquote by hand, and now we update our guess with 1.7699, we would end up calculating 21.2249 for the reactor feed, 2.9766 for our reactor effluent, and 1.78 0.59 for our NA1 calc. These values are now quite close, right? We took our updated value, put it over here, and now we are at such a point where our NA1 calc is actually getting pretty close. In just 3 iterations, we're very close to our guessed value. And so our convergence vector here would be these 3 numbers. If we were to sketch that on a plot, that would look something like this. So a quick sketch of our convergence plot, if we're using NA1 calc as our value and our iteration here, and we have 1 iteration, 2 iteration, 3 iteration. The first one was here. The second one, we had a smaller change, and by the third one, it was even smaller. If we continue these iterations out into this space over here, presumably this line will level off, and that will give us our resulting value. So let's see how we would set this up in MATLAB as well. I'm not going to go over too much detail as to where these equations came from, because these are coming from our previous homework problem, so you can always review that homework solution if you're not quite sure where these came from. So I've already got the general setup over here. Let's go ahead and close that window really quick. I've got a few constants defined up here at the top. These were from the problem statements. And then I've got the similar setup for the for loop set up here. And then down here is our plot in order to get our convergence profile. And then finally, this is our local function specific to our particular problem, right? This was our problem that we're going to provide to fsolve in order to solve our reactor. And so all of the syntax for that is coming from the previous homework problem. I'm just interested in how do we set this up for successive substitution. As we did before, we have a few parameters that we need to set. Let's count our number of iterations. How many steps would we like to do? About 10. The number of NA calc values that I suspect that I will get is also 10, but they're going to come out in a vector. So I want my vector to be 10 by 1, or just generally have as many entries as there are iterations. And then I need a starting value for NA1 guess, which, as we saw before, was going to be 0, right? We don't know how much it is. You can change your guess if you want to see if it's stable or not, or if it's particularly sensitive to your initial guess. The material balance on the mixing point was our first material balance that we had to do, and this is equal to NA0 plus NA1 guess. Right, we had 2 things that were just merging together. We also had to calculate a new value of our flow rates, which was, again, specific to our particular problem, so this may not come up on every problem. And our volumetric flow rate entering our reactor was just the sum of those 2. So those were all material balances on our mixing point. The material balance on your reactor, this comes from our fsolve. So the syntax here, again, I'm going to refer you back to our homework solutions if you're not sure where these are coming from. The extra inputs are handled in Chapter 1, so if you're not familiar with how to provide extra inputs, you can go back to Chapter 1. And then we have to provide an initial guess for what we think the solution ought to be. Our initial guess for what's coming out of the reactor can just be whatever's going into the reactor, which is Na2. That guess is different from the guess for successive substitution. This was specific just because we have to use fsolve. If we didn't have to use fsolve, we may not have needed that. Our material balance on the splitter, whatever is coming out, is that Na4 needed to be 0.4 times Na3, but maybe we didn't actually need that. The value we're really more interested in is NA1 calc. Remember, we're going to assign this to the ith location of our NA1 calc vector, and that's going to be equal to 0.6 times NA3. Again, if you don't know why it's 0.6 or something like that, just review our problem statement from that one. The successive substitution portion of successive substitution is that we now need to update our NA1 guess to be equal to NA1 calc of whatever we just calculated, right? The ith value of our NA1 calc. And so now if we go ahead and save this and run it, I'm going to have to dock our plot over here. We got absolutely nothing because I must have messed up one of my plots down here. There it is. My plot was not, oh no, that was the correct one. Let me see. Let me pause this real quick and find my typo so you don't have to sit here with me. Okay, I found my two typos. I had incorrectly put the feed as the outlet, and then I had incorrectly said that I want a matrix instead of a vector. So let's go ahead and update that one. Go ahead and dock this plot. And what you can see is that we have converged pretty quickly, right? After about 5 iterations or so, the value for NA1 calc has stabilized at what we would call the solution value. So again, the general approach here is sort of sequential, right? We make a guess. We use that guess to calculate our material balance on the first unit, material balance on the second unit, material balance on the third unit, material balance sort of as a process specification, this was our process specification, and then we update our guess, right? And we just keep going through that iteration procedure over and over and over again. And then we plot our convergence profile over here, and that gives us a plot like what we see over here. And we just run that until we decide that, yeah, that looks stable enough, right? If I change my number of iterations up here to 20, not very much has changed, right? It's still pretty flat. This is particularly useful on your project because on your project, you've got a system that looks almost identical to this. So if I just briefly update you with the nomenclature that you've got in your project, the project will have a similar set of units. So you'll have your main bioreactor, your aerator. You'll have your settling tank called the clarifier over here. You'll have fresh feed coming into this. Your clarifier will produce an activated sludge stream, some of which goes out, some of which is recycled back, right? And in the project statement, this stream is given as a 7. So how would we go about solving this with successive substitution? We're again going to break that recycle stream, right? So it's no longer here. Instead, you're going to have a value over here and a value over here. This one becomes our stream 7 calculated, and the one over here becomes our stream 7 guessed. So you'll guess a value for stream 7, use that, run through your entire analysis this way until you come back over here to 7 calc, compare 7 calc to 7 guess, and keep going until this thing has converged. Notice that you'll have more than one component, which is totally okay. If your 7 guess includes a guess for species A, species B, species C, all the way up to species Z, that is totally okay, right? You'll just have to guess a value for each one of those. You can guess a value of 0, 0, and 0 for all of those. Each time you do that, you will calculate a corresponding number of calculated values. So NA, NB, NC, all the way up to NZ. And those will obviously be non-zero, and then you will use these values to update your guess values and continue in that iteration. So I hope that was new. I hope that you will find it interesting, not just in this class, but elsewhere. But you will probably find it exceedingly useful on the project, partly because I've actually asked you to do it. So I hope that was helpful. Please let me know if you have any questions, and good luck on your project. Let's go ahead and turn off this recording. Good luck all.